and the idea of a control volume. Let me give a very simple example. So say you have a piston. This is a piston and these are the walls. Okay, let me just draw the piston with thick walls. No problem.
Good afternoon, sir. I have joined just now. Can you please start it from starting?
I mean, I've not started anything important as such.
Okay, sir.
It's a very weird way to join the meeting, but okay. Let's say we have piston like this. So this arrangement, you have a plunger like this, and you have a piston like this, and say this is some kind of gas, and this is loaded on top by some weights. Okay, so now we want to analyze the system. To analyze the system, what we can do is we can consider that whatever this gas is of our interest. So we will say that this particular boundary is the control volume. And obviously this shares the same idea as what we had learned in fluid mechanics. Control volume can deform, can allow for fluxes, all right, and it can allow energy transfers. Okay, so what do we mean by the first point when we say that it can deform? Say that I now take a Bunsen burner, okay, and I light it on fire. Okay, there's a flame. So now what do you expect? This is the system is acted upon by the atmospheric pressure by plus whatever this weight of the block is onto this gas. But as the temperature of the gas increases, the pressure inside will also increase, and slowly this weight will shift upwards, right? So let me redraw this. What will happen when after a certain while when it is heated? So it goes over here, yeah. And now this control volume has deformed. The control volume has deformed, all right? It has expanded. It can allow for fluxes. This is not the example. I'll come to that example in a while. And the third point was it can allow energy transfer. So obviously it has allowed energy transfer because we have allowed for heat to be transferred through this cylinder to the gas. This is how the heat has been transferred. All right. Now let us look at an example where the control volume does allow for fluxes. A very simple example could be an air compressor. So an air compressor, let me just grab an image from the internet. Net seems to be team seems to be hogging all the bandwidth. Okay, so I'll just try to draw it. Uh, so it basically consists of a motor, and that motor is coupled to a piston head, and so obviously it requires electrical power. It requires power in. It draws in air, so there is an inlet line. So there can be something like an air filter, and there is an exit line. This is in, this is out. Okay, so this is try to imagine it as an air compressor. All right, so now when we want to analyze this air compressor, what is more convenient for us to do? It is more convenient for us to define a boundary like this. So once you've drawn this boundary, you try to forget about everything else. So what is going across the boundary? There is some mass flux of air that is entering into the control volume, and correspondingly there is some mass flux of air which is leaving the control volume. So let me call this m dot air out, and let me call this m dot air in. Apart from the fluxes, so this covers the second point that I just spoke about. Apart from this, it also allows for power input. So work input is going into the control volume. Now you may say, I just connected to the mains. I mean, I just connected to my wall socket. How is this power in? Well, it is electrical power. Okay. Just because it is not mechanical work doesn't mean it is not work. It is. Okay. So all this also fall within the purview of thermodynamics. But apart from this, I don't know if anyone has ever encountered an air compressor. When the air compressor runs, the piston heads, they become very hot. So they start losing heat from the top. So this is heat lost. And this heat is lost to the ambient. So what happens? What do we say? That the control volume is also losing heat. Okay, so this pink surface is the control volume. So what is the difference between the first example and the second example? In the first example, the identity of the substance selected was fixed. We focused on fixed quantity of substance, while in the second example, we kept our control volume fixed. By virtue of having focused on a fixed quantity of substance, the control volume does need to deform in order to still capture all the same substance when the pressure changes or the temperature changes or the volume changes. But here there is no such restriction. The first approach is more commonly called as the control mass approach, while the second approach is known as the control volume approach. But both can be broadly classified as the control volumes. This is a closed control volume because no mass is leaving the system. So the closeness of the control volume is solely decided by mass flux. It is closed if mass does not enter or exit the system. This is an open control volume. Why? Because mass is able to come in and go out. Right? Alright. So apart from this, we have another important term, which is an isolated system. So an isolated system is a special case of a closed system. Where apart from no mass fluxes through the control volume, there will also be no energy or heat. Heat or work transfers will also be not there. Okay, so a thermos flask is a very good approximation of an isolated system, but it is still an approximation of the system. Okay, so what do we have? Oh yes, so this surface, this imaginary surface that we have drawn, this surface, the bounding surface of a control volume, it is known as a control surface. I mean, just to be thorough. Of course, none of this will have any bearing, but you should still know this. Let me see if the actual compressor image has finally come up or no. Oh, yes, it has come up. Let me see. Oh yes, this looks good. Copy. All right, so this is an air compressor. Okay, these are the power connections. The two holes you see, one of them will be the inlet. Actually, on the other side also one will be inlet and one of them will be the outlet. I mean, actually that configuration is not fixed, but whatever. And there are fins. If you look closely, you will see these serrated structures on the top. Do you see those? These are known as fins, and they are there for passive cooling. I'm sure everyone has seen a set of fins somewhere in their lives for passive cooling. Can someone give me an example?
Radiator.
Yes, it is there in a car radiator. Where else?
So this fin-like thing would also be found in case of to avoid eddy currents.
To avoid eddy current, that thing is called as a stamping. That is something else. That theory is something else. No, here we are more focused on heat transfer. It is there in your CPU as well. The CPU coolers have those fins. Okay. Okay. So apart from this, there is a big cooling fan. So this wiring goes to an electric motor. So this region contains an electric motor, an induction motor, and by the looks of this, it's gonna be a single phase induction motor. So air is drawn by this fan, and there is a similar fan on this side as well. So air is drawn from here, and it flows over the coils of the induction motor, and the air is thrown out through these holes. If you can observe these holes, this hole, this hole, this hole. Okay, so it's drawn in, thrown out. All that in order to keep the induction motor running cool. Okay, so a lot of stuff has to be done. So you can see that there is work, rather, yeah, there is work input in the form of electrical energy. There is mass flux in, then there is mass out. Okay, a lot of stuff going on. Then there is cooling air in, mm, cooling air in, then there is cooling air out. Okay, a lot of stuff going on. So the control volume for such an analysis would simply encompass the entire object into consideration. Okay, this would be the control surface. Right? And this entire thing would be the control volume. So is so far so good, no doubts, very easy. Any doubts?
Sir, uh, sir, am I audible?
Yes.
Sir, regarding control mass and control volume. So, based on what you have explained just before, can we use them can we use them simultaneously or?
No, you should never have to use it simultaneously, but you can use either of the two approaches. So, okay, let me just take this to a whole new level. Let me redraw an air compressor, and I'll show you how you can analyze the problem. So let's say that this is an air compressor. Forget about the internals. In thermodynamics, you hardly bother about the internals. This is an air compressor. Let's say there is a tube going in, large tube going in. There is a tube going out. Okay, so this is air in, this is air out, and obviously there is work is going into the system as well. So this is power basically. Okay, rate of work. So first approach says I'll just make this as the control surface and I can analyze. So when I choose this as the control surface, my focus is on evaluating the different parameters of the air compressor. I'm not really more bothered whether what is coming in, what is going out. I know that air is coming in at certain conditions, air is going out under certain conditions. Suppose I want to know how much work this air compressor will require or how much heat will it be losing, stuff like that. So now in this particular control volume, this air compressor is in focus. But then I say, no, 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 no. I have the problem reversed. I say that the air compressor does consume so much amount of power and the air compressor is giving so much amount of heat and air is coming in at so much kg per second. What I can also do, but I wouldn't do it, but I can track a certain amount of mass like this as it travels through the air compressor and goes out. So obviously when it goes out, the air will become hot and it will be compressed, so the control volume will shrink. Okay, whatever this volume is, say this is V1, this is going to be V2. Why have I drawn it smaller? Why have I drawn the volume smaller, guys? Anyone?
The compressor does the work.
Well, so the compressor literally compresses it. So it increases the pressure, reduces the volume. So if you were to imagine a small volume of air entering into the compressor, it would come out even smaller coming out of the compressor because it has been squished. Is everyone able to follow whatever I'm saying?
Yes, sir.
Yes.
I mean,
Yes, sir.
I want to get a nod from everyone. Otherwise, there was some guy in the previous fluid mechanics. He said that sometimes he was getting high BP. So I hope that guy is recovering well. So where was I? Yeah, and
Sir,
why have I told it?
sir,
Yeah,
in this case, you are taking the small amount of air as the whole system and analyzing it.
yeah. So this is now the control mass.
Okay, okay, understood.
So if I now track the control mass, what is going on? The control mass is being acted upon by this much amount of work. That control mass will lose this much amount of heat from here, and it will come out at certain higher pressure. You see the point, right? And higher temperature. The pressure will be higher, the temperature will be higher. We will come to concrete examples. I'm just giving you an example where you need not just stay confined to a control volume, or you only need to use a control mass. You can use either of the two, but you will often find, based on your experience, that for a certain problem, it, it, it will never make any sense to attempt it from a control mass or vice versa. In certain problems, the problem will be just a few lines of calculation if you do it using a control volume. For certain problems, it will be just a few lines of calculation if you do it using control mass. And it will be quite obvious. You don't need to really say that, oh, how do I know what to use, where to use. It will be very, very obvious. Okay. Alrighty then. So we're half an hour in. So does that sort of help clear the air, everyone?
Yes, sir.
All right. All right. All right. So let me make a new page. What was the shortcut? I forgot. Control D. All right, so now let us move on to the next important concept, which is properties and state of a substance. And we will come, rather, we will go deeper into this properties of a substance in the next coming classes, because we will be studying what is very important, and it is known as properties of a pure substance. But for now, I'll just give you a broad overview. So, let us start with an example. Let us first know what a phase means. Okay, so loosely speaking, phase means a certain homogeneous, uh, how do I say, a homogeneous matter. So say we say that water, you have liquid water. So this is closed, this is pressure cooker, and when you heat it, you say that when all of the water becomes steam, what will happen? You say that the liquid phase has become into gaseous phase. Okay, so phase is basically quantity of matter in a homogeneous state. And so there can obviously be a phase boundary. So even before all of the water has not become steam, there is like a boundary where this is steam and this is liquid. This boundary is known as the phase boundary. Pardon me. Yeah, sorry about that. So where was I? Yeah, and in a system there can be multiple phases that exist, and you all have heard about what is known as the triple point and all that. But we will go into more details when we study about the properties of a pure substance. Okay, now given these things, so how do you actually sort of declare that, okay, now I have liquid water, or now I have vapor, or I have ice? How do you pinpoint? I mean, how does someone do that? You must have like some identity card or something, right? For everything, there has to be something which it possesses, which will tell you, and that thing is called as the state. Okay, so a state of a substance, well, what I said was not entirely correct, but just hear me out. The state of a substance, it may be defined, okay, it may be defined or described by certain observable properties. And can you give me some examples of observable properties?
Volume.
Volume is one, yes, that is not incorrect. Pressure, you can observe that as well.
Temperature.
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 Temperature. Well, you said volume, but a more appropriate thing would have been density, because yes, I mean they are related through the mass. So you stand correct. Now, how many of these properties do you need to completely define the state of a substance? Sometimes that becomes the main question. It's like an Amazon delivery guy telling you where to deliver this. For some of you, maybe it is so obvious, you can say that there will be a Hanuman Mandir, just take a right and you will see my house and you will get the delivery. But for a campus delivery, for example, the quarter number, then this, that, opposite BSRC, yeah, many things. So how many specific parameters do you need to completely define the state of a substance? This is an important discussion which will happen in the properties of pure substances. Okay, so when we will study that, you will see how beautiful it is. But more generally, thermodynamic properties, so these properties can be defined as intensive and extensive. Okay, so I'm just gonna make this a bit larger and say etc., because this is not the end of it. And in general, such kinds of properties can be declared into two classes. One is the intensive property and one is the extensive property. So an intensive property is something which is independent of mass. An extensive property is something which obviously varies directly with mass. Right? So if a quantity of matter at a given state, okay, so you are at some state, say you are in liquid, and at some state, say some temperature, some pressure, some density, and you take a chunk of it and you divide it in two, so each of them will have the same intensive property. Okay, because the intensive property is independent of the mass. This is not actually being split, this is split in your mind's eye. Okay, an extensive property such as the absolute volume, it's literally getting halved. Okay, so the extensive properties and intensive properties, and obviously you have studied this in your class 11, and I don't think I need to elaborate a lot on this anymore. So now, throughout our studies, you will also see a very popular trick, that if you have an extensive property, so obviously mass is an extensive property. Why is mass an extensive property? Because mass obviously depends on mass. Okay, so how do you convert mass into an intensive property?
Mass per
Divided by
unit
mass.
volume.
So divided by volume, right? Well, the inverse is what is typically done. So suppose you have the volume, total volume, when you divide it by the mass, you get what is known as the specific volume. And it is basically 1 over density. So in fluid mechanics, you have a lot of discussions with density, but in thermodynamics, you will have a lot of discussions with this specific volume. Okay. Apart from this, there are other things as well. So there can be any quantity x, and it will be capital X over small m. So small m is the total mass. So if capital X is the extensive property, you can simply make it into an intensive property by dividing it by the mass, and so small x becomes the specific quantity. In this case, it was volume, and then it became the specific volume. I'll just give you an example. Small h equal to capital H over m. Capital H is the enthalpy, small h is the specific enthalpy. Okay, we'll get to these, but I just thought you should know this. All right. Now, what should we discuss? How much time do we have? Okay, we have 20 more minutes. So, what all have we discussed? Properties, state, phase. So, let's study about processes and processes. So, when a certain control mass, suppose you're studying a control mass, and this is not just true for a control mass, it is true for a control volume as well. So suppose this control mass is at some pressure, some temperature, say P1, T1, and you've acted upon it by some work or given it some heat, right? Given it some energy basically, and now it has gone from this state to say this state, and its pressure temperature is P2, T2. So its state has changed. I mean, forget the location. The location is not important. It could be at the same point, but I'm drawing it at two separate locations. But now you have affected a change of state. So in order to change state, you must do something. You must do some work, or you must transfer heat. Okay. So now, what kind of process has taken place in when going from this state to this state? Now here is the important part, which is sort of an assumption in the entirety of engineering thermodynamics, and this is a very important concept. But even if you do not grasp the concept entirely, there is no other way for you to attempt any problem at all. So even knowingly or unknowingly, you will make this kind of assumption. That's much I'm sure. So that is the beauty of this assumption. There will be no other way for you to attempt the problem. So say this is piston cylinder arrangement, and say this is a stop. So what is a stop? It's like it does not allow the piston to fly off. Okay. Otherwise it would simply fly off. So this is the piston, this is the cylinder. All right. And this is the gas. Oh. And say it has a lot of thin discs, like a huge number of thin discs. And what you can do is you can pick up one disk at a time. Okay. So what's going on? When you pick up, so suppose I can shift everything a bit further down. Yeah, the stops are over here. Yeah, say this is the original system. Now what do I do? I remove one disk. Then the pressure on top has reduced ever so slightly, but the gas pressure is still pushing, so it wants to be in equilibrium. So before removing the disk, the inside pressure was due to the entire set of mass. Suppose this piston is friction free, is mass free. So whatever pressure was there, it was solely because of the weight on top of the piston. When you've removed this, you've lessened the load. So obviously the inside pressure is also trying to reduce. How does pressure reduce? When volume increases. Okay, for a gas, you can cause the pressure to reduce when the volume increases. And how will the volume increase? When the piston tries to go up. So the piston moves up ever so slightly. All right. Now you remove another disc. Again, small upward displacement. So keep doing this, and slowly you will see that the piston finally reaches this spot. Okay. Now, in yet another experiment, what you can do is, you say you are not a very patient person. You just grab hold of all these discs. You just take them out in one go. Okay. You just grab hold of all these discs. You just take them out in one go. What will happen? Maybe the inside pressure is so high that this piston will just fly off and hit the stops. Okay. Say because of inertia, it may you can imagine it like an explosion. The inside pressure is high and suddenly the outside pressure has been made zero. This piston will be thrown upwards, so it will hit the container. So there is no way for you to predict how this piston has gone from this position to the top position. Okay, so let me just try to conceptualize this furthermore. Let us try to make a plot. Say say that this is x, and on the y-axis we have pressure, and it is at a certain initial location, say x naught. So suppose this is x naught, and it's at some pressure. So in the first experiment where you're removing one disk at a time, suppose that the entire process is isothermal. We can also assume that process is isothermal, meaning that at any given point the temperature of the gas is not changing. Then how will the E versus X curve look like? Anyone wants to guess?
Hyperbola.
It will be a hyperbola. And why did you say so? Is everyone sure why this is going to be a hyperbola?
Yes, sir.
Well, so basically you can simply take the area of cross section of this cylinder, multiply it to the x coordinate. Okay, so this entire thing simply becomes the volume. Okay, so P versus volume we are plotting, and for isothermal processes, for an ideal gas, mind you, it is going to be PV equal to constant. Okay, that is the reasoning, that is the logic. Okay, good. All right, so when you do this slowly, you will obviously go along this. You're taking many steps. So each of the point you're noting it down on the graph paper. You're going very slowly, you're going, no sudden movements. And finally all the masses have been removed and you have come to the final position. Very good. Now comes the impatient guy. what does it do? It just takes all of the masses and it just removes them. So suddenly what happens to the piston? It gets lifted, so suddenly there will be a much lower pressure. So the pressure, so it may look something like this. So what will happen? So suppose the final equilibrium position is somewhere over here. Okay, so this is the final equilibrium position. This may fly off. When it flies off, the pressure will be very low. So this is the X stop. So what can happen is it can suddenly, it won't go in a straight line. I will always draw it with a dashed line. It may go to the stop. Then it can go back and maybe finally converge to this location. You don't even know what's going on. Maybe it does this for all you care. Okay. So what is the fundamental difference between the process 1 and process 2? So process 2 is absolutely irreversible. And you have no way of telling what state points did the system take in order to go to the final state. And in the first, it is known as a quasi-equilibrium process, where you can sort of approximate that you have removed the disk and let the system go to equilibrium. You have waited a while, then again removed the disk, then again waited a while for the system to go to equilibrium. No sudden movements, nothing. Okay, so this particular thing is called as a quasi-equilibrium process. So now you may say, okay, wow, later on you will see that even air compressors and all you can approximate as quasi-equilibrium, no one cares. But see, I mean, what decides how quickly the relaxation is going to be? And then you have to really go into statistical mechanics. So how quickly a relaxation is going to be, it depends on the nature of the gas and many other things. But this is much beyond the purview of this course. But like I told, if you do not know how this curve looks like, you will never be able to solve a problem. So you will approximate it as this. And that is why I said, regardless of whether you know this or not, you will make this assumption. So we have a few minutes left. One last thing I want to yeah, so this state, okay, this is the final state. So in both the curves, this went from here, it bounced around, and finally it also went to the final spot. So once it does go to the final spot, this is the final resting spot, final resting zone, resting spot. You have no idea of telling whether the process that happened was an isothermal process or some horribly irreversible process. Okay, so that's the beauty of a state. So the state is solely defined as it is. It does not depend on how it got to that particular point, and so they are path independent. Okay, this is something which you might have also uh, looked at in your class 11 or 12th. Okay, so the property is something which only depends on the state of the system and is independent of the prior history. Okay, so over here the pressure, volume, whatever you define it, that is sort of independent of whether you took it slowly or very quickly. Okay, so what kind of properties do the, I mean, they're obviously called as state properties. You recall this? Do you recall such a thing, state property?
Yes.
State property. All right, so I guess that is it from me today. And yeah, let me just turn off recording. Don't leave yet.